Hi again, welcome to part 2 of acceleration. In this part I'm going to start talking about the graphs of acceleration, specifically our velocity graph here. So previously in physics, I hope you remember that this blue box right here represents motion going in the positive direction. So any line up here means it's moving forward. And if you look at this pink box right here, anything moving backwards is located here. So, oops, I got ahead of myself. So remember, acceleration means a change in motion. So just for an example, in order for our motion to change in this graph, we need to have a slanted line, a change of velocity. A horizontal graph, which I won't model here, anything that was horizontal would not be an acceleration because we didn't change our velocity. So let me show you the different ways that we can actually model acceleration in a graph. So notice here, this is speeding up forward. That's because we're starting here and we have a zero velocity, and then over here we have a greater velocity that's positive, so we're speeding up. Now since the line is in this blue box, it's a speed up forward. Continuing this line, if I go the other way, it's a slowdown because I'm starting from a faster velocity and going to a lower velocity. So the number value tells us if we're speeding up or slowing down. So this could be like 10 and this could be like 2. And interestingly enough, we forget, but this line right here, this dark line, means 0. So anytime velocity or a line crosses this line, it stops. I mean, right now, yes, it's not actually crossing the line right here, so it didn't stop. It's actually still moving there. But over here, that's a 0 velocity. So if we look at the next two examples, so we have a speed up forward and a speed down forward. Okay, so interesting, right? So this first one, number 1, can represent like a car at rest and then going. So you're at a stoplight, you're waiting for it to turn, and then it turns, you step to the gas pedal. That's what your graph would look like with constant acceleration. Slowing down forward, so you could be moving toward a stoplight because it's marked red to stop. So this could be that case, right? So you're moving forward, but you're slowing down. So that's an interesting, perspective there. Now look at this line. It's definitely different. So this line shows that we have a greater velocity because even though it's negative, the number's bigger. So negative 10 is bigger than negative 1. So what we have here is you're actually slowing down. And since we're in this pink box here, whoops, we're going backwards. So we're slowing down backwards in this. So slowing down backwards, so you're backing out of your driveway. Or you're doing a K-turn, so you're backing up and then stopping. That's what that graph represents there. But this one, we're starting at rest and then moving backwards. So this could be like you're in your car, you're sitting down, you put it in reverse, you hit the gas, and you go. So that's speeding up backwards. So those are some real-life examples of this. So I purposely did this because even though they make the same shape, they mean different things, right? This one's a slowdown, but this one's a speed up. This one's a slowdown, and this is a speed up. So the shapes of the graphs get confusing. So that's why, well, I'm not trying to confuse you. I'm just trying to make you aware of these situations. And also, I always think that because of the distance versus time that this means backwards, the negative slope. That's not true. So you really have to pay attention to this. This is key because this type of graph tells you how to interpret things the right way. Otherwise, if you treat this like a distance versus time, it has its own set of rules. So you really have to be careful with this stuff. So biggest things is this is a constant acceleration because these are straight lines. Now your AP, your homework may give you curves, right? Because real life doesn't stop abruptly and go off in curves like that. But just be aware that we're always going to, in the AP, deal with constant acceleration anyway. We're not going to do anything different with that. But if it's not a perfectly straight line, then you can model it as a straight line. Make it simple. Slowing down points toward the axis. Both cases of slowdowns point toward the axis. So this is a slowdown, remember? And this is a slowdown. So they always point toward, which means speeding up is away. So this is a speed up, right? Speed. Like that. So those are some tricks for you. Negative. Remember, this is so big, and it confuses me all the time too. So, you know, -8 is faster than -1 because 8 is a bigger number than 1. 8 is bigger than 1, right? Okay, so I don't actually know how to. I want to keep the ink, discard. Okay, I think that's how you do that. Learning here. All right, so take a second and interpret this graph. So if you need to stop the video to do that, you know, take a second. But I want you to think about what's happening here before I explain it. So press pause, think about it, and we'll come back. Okay, so I assume that you did that. So let's talk about it. Anytime you have a complex graph, break it into parts, because if I analyze this whole line as is, it's going to be difficult. So let's break it down. So I see that I start here, and then I come to 0. This is a positive velocity. This is 0. So if I go from positive to 0, that's a slowdown. And I'm moving forward because I'm up above the positive x-axis. So I'm moving, so I start off moving forward, I stop, so that's v equals 0, and then I start from 0 and I increase my speed backwards. Because I start from 0 and I go to a non-zero value there. So what would represent moving forward, stopping, and moving backward, right? So before I even do that, this is a change of direction, right? I mean, that's how you would change direction, is you have to stop. So anytime you have a line crossing here, just go with it. I'm just going to make up another line. If you have a line like this, this is a change of direction, right? Backwards, forwards, 0. So let's scribble that out for a moment, and let's talk about this. So what can be moving forward, stop, move backwards? If I made a distance versus time graph right here, it would do this. So I'd start moving fast, and then I'd slow down like that. So this would be rest at the top here. This is a speed up forward, and this is the speed a speed up backward. How do I know? Because we have rest here. Okay, so I go from moving to rest, and I go from rest to moving. There's a positive slope here, which means I'm forward, and I have a negative slope here, which means I'm backwards. This models a ball being tossed in the air, which is a common model in physics. So if you take a ball, let's see, I don't have a ball, we can use this already. Let's see, I'm trying to get in the video here. Maybe a little lower. I have a little lag, there we go. That graph is me doing that. So it totally doesn't match the motion, right? It didn't make that curve. That's the position versus time, which is on the bottom right here. What we did was model the change of motion, so the acceleration. Now, a really cool thing about this, I think it's really cool, is that this line is constant the whole time, right? So notice that if I calculate the slope here, the slope is still the same down here. So the motion of this object in terms of acceleration is actually constant, despite the fact that it went down to the middle line. So if I calculate the slope between these 2 points, it would be the same between these 2 points. So, for example, like I used, like the ball being tossed in the air, it's undergoing a constant acceleration. Well, what does that sound like? It sounds like gravity, right? Well, maybe you didn't know that, but that's really cool, right? So an object that's accelerating up, an object that's being thrown up and down is constantly feeling the pull of gravity, and that value is a constant value. And spoilers, that value is negative 9.81, which I'll prove to you in another class. So very cool. Negative means it's being pulled down. Okay, cool. So interpreting graphs, very important. I do not want to keep my annotations. Oops. Okay. So here we go. So we're looking at a position versus time graph versus, yes, a position. Sorry, I confused myself here. So I wanted to show you constant motion versus changing motion to show you how the position graphs change, right? Constant motion has a straight line. Changing motion has a curve. So if you look at this, here's a velocity and position. We start off at 0 here, and we go to some positive value. So on a position graph, the instantaneous slope is the speed. So notice anytime you have a flat line like that, the slope is 0, which means 0 speed. But then my slope over here changes, right? It's more steep. So that means we went from 0 to some value, so we were speeding up. The forward comes from the slope. Notice that it's a positive slope. So that's moving forward, speeding up. Now you try. So you have a graph right here. Take a second before I give you the answer, so you might need to, stop the video again, but try to guess what this is what's happening here. Okay, so the analysis would be you have a slope here and no slope here. Slope means velocity, no slope means 0. Positive velocity to 0 means you're slowing down. And that's true here. We have a positive velocity and 0. So we're slowing down forward. So, and notice that the forward motion, even though we're slowing down, the slope, the average slope, clearly slope changes, but the average slope is positive, which makes that a forward motion. Speeding up forward, slowing down forward. They both have the commonality is this positive slope, which represents the motion of forward. Take a look at this. We're going backwards here. So I can look at this and say that I go from having a velocity to 0, so I'm slowing down here. And look at that. 0 slope here. Negative slope here. I'm slowing down backwards because the slope here is negative and plus the value here is negative. That's a backwards motion. I have a 0 here. I have a negative v here. I go from 0 to negative v. I'm speeding up. 0 slope here. Negative slope here. I'm going from 0 to a value, so I'm speeding up, but the slope tells me it's backwards. So those are those are all the different ways we can display our acceleration of speeding up or slowing down on a position in a velocity graph. We could do more with graphs, it turns out. So we already saw that, for example, distance versus time, the slope of that graph is speed or velocity. You can interchange that for a moment, okay? So we can also look at that in terms of acceleration. So if we have a velocity versus time graph, and we calculate the slope of that, we'll find the slope is going to be the calculation of acceleration. So just to show you, sorry, I know I'm working on here, but so the change in y over the change in x is going to be, in this case, the change in velocity over the change in time, which I hope rings a bell, is by definition acceleration. So the slope of a distance versus time graph is velocity, and the slope of a velocity versus distance graph is an acceleration. And the signs of the slope give you the signs of the object, so whether it's a positive or negative acceleration or positive and negative speed. So this would be a positive acceleration because the slope is positive. So now what we can do is look at an object's area. Cool, right? Let's look at this object's area. So if I did, say we have a constant velocity. You have to excuse my non-straight line that's supposed to be straight. and I take the area. So the area would be, for this, would be the change in velocity, and this would be a change in time, right? So if I took this measurement and this measurement, so I'm getting the area of this, sorry, it's supposed to be straight, it's not great. But delta V times delta T equals, well, what? Well, excuse the mess here, but if you notice, delta V equals delta X divided by T. If I solve both sides by T, sorry, if I multiply both sides by T, I can get rid of that. And then I get delta T, delta V equals delta X, because these cancel. So in other words, if I have a velocity versus time graph, the area will give me the displacement. With the similar logic, which I'll skip just because I'm just going to go a little fast here, is that same thing. We have, if you use an acceleration versus time graph, the area will be the definition of the area times time will be velocity. X versus T has no valuable area, so that is not included in here. So another thing I just got to mention here, and I'll actually use a blank screen to describe this, discard. Is the following. So say I have something like, first of all, something like this. Say I have a velocity and time graph, and this is 3. 1, 2, 3, 4. It's not pretty. That's okay. I don't think. Here, I'll put myself back in the view. So it's not very pretty, but you can see that if I want to know the displacement, which is a common question, right? So say I have, sorry, this is really bad. I don't even have units here, but that's okay. So say they give you a velocity time graph, and they give you a question that says, what's the displacement? 90% of you will look for an equation. It's just like what you're like bred to do, or your first thought. So I would say err on the side of caution. Well, not even err on the side of caution, but use the graph instead. So in other words, you could say, oh, I don't need an equation. I can just use the graph. So I know the area. So this area here is going to give me my change of displacement. So the area is going to be delta V times delta T. And when I do that for this example, delta V would be 3, just using a number for you, times 5, 15. Now you can see hopefully that the units, these will cancel and you're left with meters. So there you have it. So just a note about this displacement that we just calculated is this gives us the change is 15. It doesn't give us a starting position, an ending position, because we can go from 0 to 15 and that's a change. I could have gone from, 15 to 30. That's a change of 15. Or anything in between. So this is just giving us what our changes, what is our displacement, not a reference point. So that's one big thing I just want to talk about. Next, I want to talk about another example. So maybe you might have something like this, where you have a graph like this and like that. This is time. This is velocity. And then let's go ahead and make that. So close enough. I kind of want to make these different values. My scaling is terrible, so sorry. But let's make this 2. Let's make this -3. Let's make this value 3, and this value 6. Okay, so 1, 2, 3, 4, 5, 6, 1, -1, -2. Same question, what's delta x, right? So when you're dealing with this, or anything complicated other than just one shape, break it up into shapes. So here we go. See this right here? I'll solve for this area first. But the point I wanted to make, and I didn't emphasize it in the last part because I just want to demonstrate the area calculation, is signs. If you're above, this is a positive area. So guess what? If you're below, it's going to be negative, right? We're going backwards here. Just like that. So, how do we calculate this? We're going to find the top and add the bottom, but technically we're subtracting because it's negative. So let's go ahead and do that. So this one, 0 to 2 and 3. So this is delta x up here is going to be 2 meters per second, because that's the change in delta v. Change in t is 6 meters for the top part. For the bottom part, I'm starting at 3 and going to 6. So my delta t is 6. And I'm going from here to negative 3. So notice I'm taking the absolute value. So I didn't take 3, but I took from here to here. Not absolute value, I'm taking the value. So it's not 3, it's not 6, it's the difference between those. So delta x here is going to be delta v times delta t. Delta v is negative 3 because we're below. And also these values are negative. And then it's positive 3 seconds. Negative 9, so then we do the sum of those, right? So I'm going to squish it in here, sorry. So the delta x is going to be positive 6 meters minus 9 meters equals minus 3 meters. So the answer to this example is the fact that this thing is displaced 3 meters away from the starting point, so behind the starting point. So that's how you would interpret that. It's behind because the negative and the value is 3. One more point I want to make. What if you have a graph like this? Right? Lots of things happening here. Sure, we'll go with it. So, if you have a complicated graph, break it into sections, okay? It's so much easier. Also, remember that when you take an area of a geometric shape like this, that's basically a triangle. So the area of a triangle is going to be 1/2 base times height. So when you calculate something like this, you have to use the area of that geometric shape. So let me just actually clear this. I'm going to redo this and do a different one. So let's do this one actually. I will actually do this one. This is really complex. Sorry. But if I put some values to this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It will look something like this. So I would break it down into shapes like that. I'd find the area of part 1, part 2, part 3, part 4, part 5, part 6. These will be negative because they're under. These would be positive because they're over. Now notice that these shapes right here, I broke into squares and triangles because they're just easier to solve. So you would do the same process, so the delta x would be the sum of all the parts. 1, 2, 3, 4, 5, 6. So I won't use numbers at the moment to show you, but that's how you would solve something very complex. I will definitely put a question like this in your test to see that you picked up on this concept. So using the area, of course, we're looking at velocity versus time. This all solves for displacement. Now, if I change the axes to acceleration in time, it would solve for velocity. And same rules apply. If you find, if you have an acceleration graph, so if you have an acceleration graph like this, the area gives you the change in velocity, not the starting and end points too. So your velocity changes by 5 meters per second, positive. Same thing, you can have a negative area, so you can have a negative change in velocity. It means backwards. So there you have it. So this is called the ladder. It's a learning technique you can use. It's alphabetical, so it starts with A, V, and X. When you go up the ladder, you take the slope. So if you go from X to V, to go to X to V, you have to take a slope. So if you have a distance versus time graph, taking the slope gives you velocity. And if you start on a velocity graph, that's going to give you an acceleration if you take the slope. And if you go down the graph, or down the ladder, if you go from acceleration and take the area, it gives you the velocity. And if you're on the velocity graph and you take the area, it gives you the displacement. So it's a little way to help you solve for some of these problems. So these are 2 examples of solving with graphs. The answers are in the PowerPoint, so you can check your answers. But like I said before, break them up into parts. I would take this and I would do part 1 and do part 2, find the areas of those and add them. Same thing, I would take the area of these. My shortcut actually, by looking at this one right now, is that each block is 10, right? So 5 times 2, this is a 10. Watch this, 10, this block is 10, this block is 10, that's 5, 10, 10. Another quick technique. This 10 will cancel that 10, this would cancel that 10, this displacement is 15 meters. There's a quick way to do it. So those little techniques are very helpful. So instead of going ahead and calculating all of that, like I showed you originally, if you find the block, how much one block is and look at the positive negatives, then it becomes substantially easier. Okay, so I think this slide is, self-explanatory. So, I'm not going to solve it on the video, but if you look at these, and I'll put the solutions in the notes, I'd like you to analyze these and determine the answers and see how well you do. Check the notes and see, where your understanding is. This is more of a check for you. Okay, finally, next class, I'm going to derive what is called the kinematic equation. So at this point, we're here. And quite technically, we've introduced these 2 equations. Maybe not in these official forms, but we have average velocity here and acceleration. And it turns out if I plug, for example, if I solve for, if I plug this into here, then I'm going to get this equation. And if I do the vice versa, if I take, for example, VI and plug it in here, I'll get the other equation. I'm going to save that time for class, though. Like I said, these are a little more complicated. But anyway, point being is now that we have average velocity and acceleration equations, we can make more equations to help us model the situations. In addition, we're going to do a lab that actually models this equation to see where that comes from too. So I'm going to show you multiple ways to get to these equations. And then the next step is to show you, of course, how to use them. We're going to do some problem solving with that. So I'm going to skip these for now. These are actually videos already, so you can take a look if you're curious on how to solve that. But this concludes the video of acceleration. Okay. Oops, I have to pause. Pausing.